In our previous videos, we have discussed the normal modes in case of continuous medium. And in all those videos, you have seen the propagation of vibration, or you can say propagation of waves in a continuous medium. Actually, such a vibration produces compressional wave. And what is the velocity of a compressional wave in different type of medium? That may be a solid, that may be a liquid or a gas. You have learnt. Actually, when you talk about the velocity of a compressional wave, for example, sound wave is a compressional wave when it travels in a fluid. Then in general, you have seen earlier that its velocity depends on two factors. First one is elasticity of the medium or elasticity of the material of the medium, and another is its inertia, that is density. And you know, the velocity of a compressional wave or sound wave in a fluid is given by V equal to a square root of E over rho, where actually this E is the elasticity of the medium and rho is its density. Okay. Now, actually, this formula was already known. Newton applied this formula to find the velocity of sound wave traveling in an air, or you can say in a gas. So the problem in front of Newton was what? What will be the value of this elasticity if you consider the medium is air or gas and the wave is a sound wave? So Newton only found the value of elasticity of a gas when sound wave travels through it. And when the value obtained for elasticity by Newton was substituted in this equation 1, then the result for velocity of sound is called Newton's formula. Okay? So how Newton obtained the velocity of this elasticity? Let us see. In fact, you know, when sound wave travels in an air or in a gas, actually there is a process of compression and rarefaction. You know, in case of compression, the molecules of the medium come close to one another. Okay? While in the region of rarefaction, those molecules move apart from one another. So this is the position of compression and this is the position of rarefaction. So you can say actually in gas or air, sound wave travels as a compression and rarefaction pulse. Okay. In fact, according to Newton, this compression and rarefaction in air take place very slowly when sound wave travels through it. Very slowly. And as the compression and rarefaction take place very slowly, so what will happen? In fact, you know, at the place of compression or position of site of compression, the molecules get closer to one another. So locally, the volume gets decreased. And when volume decreases, V decreases. So correspondingly, pressure will increase. Again, since volume decreases, so density will also increase. And corresponding temperature, T also increases. T should increase. But according to Newton, since this process is very slow, so what actually happens? In accordance with Newton's hypothesis, there will be a flow of heat energy from the region of compression to the region of rarefaction, where just opposite phenomenon takes place. In the region of rarefaction, volume increases, pressure decreases, okay, and correspondingly this density also decreases. So temperature tends to fall, but temperature will not fall. Only there is a tendency of falling of temperature in the region of rarefaction, and there is a tendency of rising of temperature in the region of compression. But what actually happens in accordance with Newton's hypothesis? According to Newton's hypothesis, heat energy flows from the region of compression to the region of rarefaction. And since this process is very slow, according to Newton's hypothesis, so the time for flow of heat is sufficient, and therefore temperature in the region of compressor does not rise and temperature in the region of rarefaction does not fall. It means you can say, according to Newton hypothesis, when sound wave travels through the air or gas, temperature of this medium remains constant. Or you can say that the process by which sound travels in air is an isothermal process. In nutshell, now you can say, according to Newton, sound wave travels through air or gas isothermally. And if this process is isothermal, temperature will remain constant. So this was the idea proposed by Newton for the propagation of sound wave in air or in a gas. Now applying the equation of state for a ideal gas, treating the air or gas as ideal, Newton applied the equation of a state for an ideal gas and obtained the value of elasticity of the medium. You know, if temperature of a gas is constant, then the equation of a state is given by PV equal to constant. Actually, this is Boyle's law. At constant temperature, you know, the product of pressure and volume of the gas remains constant. Although pressure changes and correspondingly volume also changes. When pressure increases, volume decreases in the same ratio, and therefore this product PV remains constant. Now as PV is equal to constant, so let us take the differential of this equation, and after taking differential you can write P times dV, that is P into differential of V, plus V times dP, that is V into differential of P, that will be equal to 0. Okay? And therefore P dV will be equal to minus V dP, and that's why P is equal to minus V dP over dV. And this can be written in this manner: P equal to minus dP over dV by V. Now see here, what is this dP? This is change in pressure, and you know, change in pressure or excess pressure is the measure of bulk stress. This is the measure of bulk stress. Okay? And dV is change in volume, and V is the original volume. So what is this dV by V? You know, this is called bulk strain. Bulk strain. And bulk stress by bulk strain, that is actually equal to the bulk modulus of elasticity, which I have denoted by the symbol E. It is also denoted by B. So what you are now observing, actually, you know, whenever this bulk modulus is defined, this minus sign exists here essentially. So in accordance with the definition of bulk modulus of elasticity, this minus dP over dV by V is equal to the bulk modulus, but it is equal to P. So you can say that according to Newton hypothesis, the bulk modulus of elasticity of the gas is equal to this pressure P. Actually, this is also called isothermal elasticity, because this elasticity of the gas has been calculated at assuming the temperature of the gas constant. So in this way, Newton obtained the value of elasticity of the gas or air, which is equal to simply the normal pressure of the gas or air. Therefore, if you want to find the Newton's formula for velocity of sound in air, what you will do? In this general result for velocity of sound or velocity of any compressional wave in a fluid, we will replace this E by P. And when you will replace E by P, then you will get a formula which measures the velocity of sound in air proposed by Newton, and that very formula is called Newton's formula for velocity of sound in air or gas. So this V will be then equal to a square root of P over rho. Actually, this result is known as Newton's formula for velocity of sound in air. Okay. But is this formula correct? Answer is no. You will see that this formula is faulty. How we can test that this formula is faulty? For this, let us try to find velocity of the sound in air at normal temperature and pressure. So let us see what is the drawback, what is the shortcoming of this formula. Actually, we want to find the velocity of sound in air or in a gas at normal temperature and pressure in accordance with the Newton's formula. And you know, when you talk about normal temperature, that means room temperature, which is normally taken 27 degrees C, or you can say 300 Kelvin. 27 plus 273, that is 300 Kelvin. And you know the normal pressure is 76 centimeter of Hg, or you can say 1.01 into 10 to the power 5 Pascal. Pascal means Newton per meter square. And the density of air at normal temperature and pressure rho is equal to 1.3 kg per meter cube. Accurate value is 1.29 kg per meter cube, which can be roughly taken as 1.3 kg per meter cube. So, if you want to find the velocity of sound in air in accordance with the Newton's formula, then use this result. At the place of P, we will write this value 1.01 into 10 to the power 10 to the power 5 Pascal, and at the place of density we will write 1.3. So after simplification we get that this velocity is almost equal to 280 meter per second. So according to Newton's formula, the velocity of sound in air at normal room temperature and pressure, that is at NTP, is equal to 280 meter per second. But is this value correct? Is this value same as the experiment says? Answer is no. Actually, in experiment, it is found that velocity of sound in air at normal room temperature and pressure is not 280 meter per second, but it is almost 332 meter per second. This may be also taken as 330 meter per second or 335 meter per second, you can take. So if you consider that the velocity of sound in air when measured experimentally, then experimental value is 332 meter per second. But theoretically, according to Newton's theory, the velocity of sound in air is 280 meter per second. Okay? Experimental value and theoretical value may be different. But the theory is called correct only when the theoretical value differs from the experimental value by negligible amount. Okay? If theoretical value agrees with the experimental value, then theory is called correct. But let us see here, what is the difference of the value of velocity of sound in air measured experimentally and measured theoretically. So the difference of the experimental and theoretical value of velocity of sound in air will be what? That will be 332 minus 280, which is 52 meter per second. This is a very large difference. It means the theoretical value differs very large by a large amount from the experimental value. So definitely there is some drawback, some shortcoming in the theory. Experiment cannot be incorrect. There may be some experimental error, but experimental error is never this much. It should be negligibly small. So definitely Newton's formula is faulty. Something there is wrong in deriving this Newton's formula. Okay. So I have mentioned here that there is a large difference between the theoretical and the experimental values that cannot be neglected and cannot be attributed to experimental error. Okay. In fact, why this theoretical value is faulty, what is the fault behind it? Newton was unable to explain this discrepancy. Okay. But after the effort of 20 years, a well-known French mathematician named Laplace successfully corrected this Newton formula. Actually, what was the fault and how Laplace corrected this, we will now see it. That is called actually Laplace correction. In fact, when Laplace tried to find the fault of Newton and what should be the remedy, what should be the correct hypothesis to derive this formula, the correction was very close to the fault. You have learnt, according to Newton, the sound wave travels in air by isothermal process. The temperature of the medium remains constant when sound wave travels. And Newton argued that why this temperature remains constant. His argument was the compression and the rarefaction takes place very slowly, and there is a sufficient time for the flow of heat from the region of compression to the region of rarefaction so that the temperature remains constant. But this was the fault of Newton. Actually, when sound travels through an air or in a gas, the compression and rarefaction do not take place slowly, but it takes place very rapidly. Very rapidly. And the temperature of the medium does not remain constant. In fact, along with the pressure and volume, temperature of the medium also changes rapidly. So according to Laplace, the sound wave when travels through the medium, then there is no flow, no gain of heat from the surrounding, or no flow of heat to the surrounding from the gas. So this is an adiabatic process. So mark it. According to Newton, sound travels through air isothermally. That was wrong. According to Laplace, sound travels through the air adiabatically. And so the use of the equation of a state PV equal to constant in deriving the elasticity of the medium by Newton was wrong. Actually, what actually happens? Sound wave travels as the compression and rarefaction pulses. In fact, in the region of compression, molecules come closer, and when molecule will come closer, volume will decrease, and when volume will decrease, pressure, density and temperature, all these three get increased. There is increment in pressure, density and volume. Density means local density of that region. volume decreases, okay, and molecules come closer. The molecules come closer. And if you are talking about rarefaction, just reverse phenomenon takes place. In this condition, molecules move apart from one another. Volume increases and correspondingly pressure, density and temperature decrease. Okay? So you can say that in this case, all these three quantities P, V and T change rapidly, but there is no loss, there is no transfer of heat from the surrounding to the medium and from the medium to the surrounding. So this process is an adiabatic process. So in nutshell, you can say, according to Newton, sound travels isothermally in air, and this was the fault of Newton. This statement is incorrect. Laplace corrected it. According to Laplace, the sound travels in air not isothermally but adiabatically. Okay? And you know, in an adiabatic change or in adiabatic process, the equation of a state is given as PV to the power gamma equal to constant. Where gamma, you know, this is the ratio of Cp and Cv, where Cp is the molar specific heat capacity of the gas at constant pressure and Cv is its molar specific heat capacity at constant volume. Okay. Now again let us take differential of this equation both sides. So when you will take differential, you will take P times differential of V to the power gamma, and differential of V to the power gamma will be gamma times V to the power gamma minus 1 dV plus now V to the power gamma times dP equal to 0. Now you can take this V to the power gamma minus 1 as a common factor. Then the remaining terms will be gamma P dV plus V dP, and that will be equal to 0. Now V to the power gamma minus 1 is not 0. So definitely this expression inside the square bracket is equal to 0. And therefore you can see gamma P dV is equal to minus V dP, and so gamma times P is equal to minus dP by dV by V. Again here this dP is the measure of bulk stress and dV by V, this is the measure of bulk strain. So this minus dP by dV, dP by dV by V, this is equal to the bulk modulus of elasticity E. So you can see, according to Laplace correction, the bulk modulus E is not equal to P, but E is equal to gamma times P. So this elasticity, which is equal to gamma times P, this is called adiabatic elasticity. P is called isothermal elasticity and gamma times P is called not isothermal but adiabatic elasticity. So according to Laplace correction, the elasticity of air is equal to gamma times P, which is called adiabatic elasticity. Okay? Because the traveling of sound, the propagation of sound through air is an adiabatic process, not isothermal process. So if you want to find the corrected formula for the velocity of sound in air, you must replace this E by this gamma times P, and therefore you can see the velocity of sound in air will be given by a square root of E over rho, but E is now replaced by gamma times P. This is actually called the Laplace correction. This result implies the Laplace correction. Now you can check that this corrected value for the expression for velocity of sound in air is correct or not. In fact, gamma, which is adiabatic exponent, ratio of Cp and Cv, its value is 1.42 for air, okay, at NTP. And you have already obtained the value of a square root of P over rho, which was 280 meter per second. You have seen earlier. So now, according to Laplace correction, the velocity of sound in air will be equal to a square root of 1.42 times 280 meter per second. And this will be actually equal to 332.8 meter per second. And you know that the experimental value of velocity of sound in air is almost 332 meter per second. This is the experimental value. And this 332.8 meter per second, this is the theoretical value of velocity of sound. So these two values are almost equal. So you can say that this theoretical value obtained by Laplace correction is in good agreement with the experimental value. And therefore, Laplace correction is treated to be correct. Okay? And so now, whenever you need the expression for the velocity of sound in air or gas, you must write V equal to a square root of gamma P over rho. This is called Laplace correction. Actually, this was a very simple calculation, and I hope you have clearly understand the each and every aspect, calculation and the concept clearly. Okay. Now, actually, this velocity of sound is affected by some factors like temperature, like humidity, like density. So, how this velocity of sound is actually affected by different parameters? Now let us see. First of all, we are talking about the effect of temperature on this velocity V. We know that according to Laplace correction, velocity of sound V is given by a square root of gamma P over rho. Okay. Now our aim is to find the value of this P by rho at a temperature T, and for this you must use the equation of a state of the gas. Now you know, for 1 mole of the gas, the equation of a state is given as PV equal to RT. What is this R here? R is the universal gas constant. You know, R is universal gas constant, whose value is 8.314 joule per mole Kelvin. Okay, this is universal constant. And number of mole is 1, so I have not written PV बराबर nRT, but simply PV बराबर RT. Now, you know that volume is simply equal to mass divided by density. Here, as we have considered 1 mole of the gas, so this capital M represents the mass of 1 mole of the gas. But you know, mass of 1 mole is simply called molecular weight. So this M is the molecular weight of the gas, molecular weight, okay? And therefore, our equation is Pm divided by rho equal to R2, and therefore P over rho, this is RT over M. So now, if you want to find the effect of temperature on this velocity V, you must replace this P by rho by this expression RT over M in this equation 1. And therefore you can see that this V is equal to a square root of gamma RT over M. Here, this gamma depends on the value, depends on the nature of the gas. Okay, R is universal gas constant. Okay. But V depends on 2 factors you can see. First one is temperature and another is the molecular weight of the gas or type of gas or nature of gas. If you are talking about a particular gas, for example, you are talking about oxygen, M will have value 32 gram. If you are talking about hydrogen, M will be 2 gram. That is fixed. In that condition, for a given gas, velocity of sound is proportional to a square root of the absolute temperature. So you can see with increase in temperature, velocity of sound will increase. If sound is traveling through air and the temperature of the air gets increased, velocity will increase. On the other hand, this velocity of sound is inversely proportional to the square root of the molecular mass or molecular weight of the gas. So in heavier gas, sound travels slowly. If you consider that there are two gases, one is oxygen and another is hydrogen. And you know, oxygen is heavier than hydrogen. So, and both are at same temperature, let us say T. Temperature of both gases is same. Then, velocity of sound in this oxygen gas will be definitely less than the velocity of sound in this hydrogen, because molecular weight of hydrogen is smaller than that of the oxygen, and that's why the velocity will be larger in hydrogen with respect to the oxygen. Okay. So this is the manner by which this velocity of sound is affected by temperature. Now, you can compare the velocity of sound wave at two temperatures in a particular gas. For this, let us consider that this V0 represents the velocity of sound wave at 0 degrees Celsius. And corresponding to 0 degrees Celsius in Kelvin scale, I have written the temperature T0. And we also consider that at a temperature theta degrees C, the velocity of sound is v theta. We consider it. Now, as we have seen that v is proportional to a square root of t. So, velocity at theta temperature divided by velocity at 0 temperature, that is v theta by v0, that will be equal to a square root of t over t0. No, t over t0. But you know, if you will change the temperature theta into Kelvin, what will be the value? That will be theta plus 273. Okay? And when you will change the 0 degrees Celsius into Kelvin, that will be 0 plus 270, that will be simply 273. Okay? So, the result will be 1 plus theta over 273 whole to the power half. Now, if you consider that this theta is very small, then in accordance with binomial expansion, you know 1 plus x to the power n, this is almost equal to 1 plus nx. This is called actually first approximation. But when 1 plus x to the power n is almost equal to 1 plus nx, only when this x is much smaller than 1. This is called first approximation. Okay? So if you consider that this theta is small, then in that condition, this theta divided by 273 will be much smaller than 1. And then according to this first approximation, we can write this as V0 times 1 plus 1 over 2 into theta divided by 273. Here at the place of n there is 1 by 2. So, V theta is equal to V0 times 1 plus theta divided by 546. Okay. Now, if you take V0 equal to 330 meter per second, or you can also take 332 meter per second. Okay, you can take 332 or 330 you can take. Then what will be this V theta? V theta will be 332 plus 332 divided by 546 times theta. And this will be V theta equal to 332 plus 0.61 into theta. So you can see, if theta is small and measured in Celsius, then the velocity of sound increases almost linearly this is just the equation of a straight line, y equal to mx plus c. Here this value will be 332 meter per second. And the slope of this straight line will be tan psi equal to 0.61. Actually, this linear variation will be valid only when theta is very small. For larger value of theta, you can see the general result is V is a non-linear function of temperature, because V is directly proportional to a square root of T. Okay? So, velocity of sound in air increases almost linearly, but only when the change in temperature is small. Now, if you want to know what will be the increase in velocity of sound when temperature is increased by just 1 degree C, what will be that? If you will take theta equal to 1 degree C, then velocity of sound will be what? This will be 332 plus 0.61. It means with rise in temperature by 1 degree C, the velocity increases by 0.61 मीटर पर सेकेंड. अगर आप टेम्परेचर को 1 डिग्री सी बढ़ाते हैं तो साउंड का वेलोसिटी कितना से बढ़ेगा? 0.61 मीटर पर सेकेंड से बढ़ेगा. ओके, बट रिमेंबर दिस रिजल्ट विल बी यूज्ड टू फाइंड द वेलोसिटी ऑफ साउंड at a given temperature theta only when theta is small. In case of larger value, you must use the general result V proportional to root T. Okay? This fact is used in solving the numerical problem. Now let us talk about the effect of pressure on the velocity of sound. In fact, pressure does not affect the velocity of sound. How you can say that pressure does not affect? You have seen that velocity of sound at a given temperature is equal to a square root of gamma RT by M. You have seen. And if your aim is to know the effect of pressure, you must take temperature constant, because temperature is another factor which affects the velocity of sound. So when temperature is constant, you can see, then by changing pressure there will be no effect on this velocity. So you can say that this velocity is actually independent of pressure. Somebody gets confused by this formula, V equal to gamma P by rho root. So some people think that here there is P, so V should be directly proportional to a square root of P. But this is not correct. In fact, when pressure increases, gas or air is a compressible fluid. So with increase in pressure, density also increases in the same ratio. And when pressure decreases, then density of the gas also decreases in the same ratio. And that's why the ratio of P and rho remains constant. Pressure will change, and correspondingly this density will also change in such a manner that the ratio of P and rho remains constant. And that is why with change in pressure there is no effect on the velocity of sound. Okay? Have you understand? I think you have clearly understand. Now if you consider that there is a fluid whose density is independent of pressure. It means when pressure remains same but density changes, if such a phenomenon will happen, then what will happen? If P is constant, then you can see from this result that V will be inversely proportional to a square root of density. So in this case, when rho will be larger density, then V will be small. Okay? And when rho is small, V will be large. Okay? Actually, this fact we will use when we will discuss the effect of humidity on velocity of sound. If you consider that rho d is the density of dry air and rho m is the density of moist air or humid air, can you say which density will be greater? Density of dry air is greater or density of moist air is greater? Commonly students gives wrong answer of this question. If I ask you that vapor is lighter than dry air or heavier, answer will be lighter. You know, and you have definitely seen that vapor rises in air. So, in fact, lighter thing rises. So, therefore, if vapor rises in air, so definitely vapor is lighter, and therefore the density of the vapor or density of the moist air or humid air is less than that of the dry air. So if you want to define the velocity of sound in dry air, denoted by the symbol Vd, that will be a square root of gamma p divided by rho d. And in moist air, this is Vm, and that will be gamma p divided by rho. Here we have assumed that both the dry air and the moist air are at the same pressure P. Okay? And therefore, the ratio of velocity of sound in moist air Vm and the velocity of sound in dry air Vd, that is Vm by Vd, this will be equal to this much. This is a square root of rho d divided by rho m. But as I have told you that the density of dry air is greater than density of moist air or humid air. So rho d is greater than rho m, and correspondingly you can see from this equation that Vm will be greater than Vd. It means velocity of sound is greater in the humid air or moist air in comparison to the velocity of sound in dry air. So when humidity increases, velocity of sound increases. Okay? So this is how this humidity affects the velocity of sound. So in this way we have completed our lecture on velocity of sound in air, Newton's formula and Laplace correction, and the different factors which affect the velocity of sound. And I hope you have clearly understand each and every aspect of this lecture. Okay, thank you very much.